Hi friends, so today I'm going to start Math Question Bank 7. So we are going to discuss 5 questions. So let's begin. I'm Dr. Ganguly. Now the first question is to find the rank of this matrix given here. A is this matrix here. All the elements of this matrix are simply 1. Now this is a very popular matrix people give in the tests and so on because it's very easy to remember and write. Remember that whenever some interview is going on, it may not be that the teacher or the person interviewing has actually prepared for that interview. So they give these questions out of their memory bank. So let's try to solve this problem first. Now, of course, looking at this problem, you can find the solution in many cases, but let's try to do it using a formal method. So let's take this matrix here, the A matrix, and let's try to use different operations on this matrix regarding the rows. So one of the things which you can do in this method, which is known as the echelon form method, is that you can try to reduce this matrix to a form which has a triangle of zeros here. So what should happen is that the row at the bottom should have zeros completely. So that's something you are targeting for here. Now, what we can try to do is, of course, in this particular matrix, we can apply the fact that R2 equals R2 minus R1. That is, I subtract the second row from the first row. And when I do that here, the second row simply becomes 0 here. So I have essentially taken each of these and subtracted it. And because all these are ones, I have got these 3 0 here. Now I again perform this particular operation that R3 is R3 minus R1 and I get all these zeros here. So now this matrix has come to the echelon form and I can clearly see here that there is only one row which is non-zero. So what we can now say is that the rank of the matrix is the number of non-zero rows in the echelon form, and this is simply 1. So the rank of this matrix is 1. Now, the rank of the matrix also is something which is the number of linearly independent rows or columns. So, of course, in this case, you can see that these are all multiple. So, it's not going to be 3, it's not going to be 2, it's going to be 1. Now, let's come to question 2, which is becoming more and more of a popular question, not only in various tests, but also in different type of interviews and so on, and that is this kind of exponential problem, that is x to the power x equals 10. And there are many students who struggle with this because they do not know a certain piece of mathematics. It's often not taught in school. So I'm going to bring that out in the next slide, which is the solution. Of course, by looking at this, you will figure out that the solution will be somewhere between 2 and 3, because of course 2 square is 10 and 3 square is 9, but you are talking of x to the power x, so it's going to be some value which is between these numbers or something like that. So again, it's x to the power x. So that's what we are going to find out now. So let's take this particular function, and what we are going to do in this equation is that naturally we will try to apply log on both sides because that's going to simplify it. So of course in all these cases I use the natural log, so I can get x log x is log 10, and then I can take this log x to the left hand side and I can write x as e to the power log x. So remember, we can do that x is equal to e to the power log x. So we get this equation here. Now, why did we write it in this form? Because there is something known as the Lambert W function. And the Lambert W function, what it does is that when it's applied on some function like AEA, it reduces it to simply A. So this function, also known as the product log, is very popular and it's there in many different symbolic manipulation softwares and so on. So if we apply the Lambert W function on both sides of this equation, I get this equation here. And then by invoking the definition of this function, what will happen is that the a value is same as log x. So I will get log x on the left hand side, and then right hand side I get W ln 10. So I raise both these sides to the power of e. So I get e to the power log x equals e to the power w log 10, and then I can simply write x is e to the power w log 10. Now I can easily calculate this w log 10 from certain websites, for example Wolfram Alpha, and the value comes out to be about 0.91876. In the next slide I'm going to give you the detailed value, but let's take the value till 5 decimal places at that point, and then of course using your calculator or your phone you can very easily get the value as x is 2.506. So this looks quite correct because something like this raised to the power of the same value would be equal to 10. So remember, if we had 3 to the power 3, that would be 27. To the power 2, that would be 4. So again, this value looks correct. You can of course check it out in your calculator or in your phone. So how do we get this particular value of the Lambert W function? Now I go to this website wolframalpha.com, and I can actually type Lambert W log of 10, and I get this answer here, which is 0.91876 and this whole series of numbers. Of course, I don't want to necessarily take all these numbers unless I am somebody who is too fastidious and meticulous, but if I take a few of them, I will certainly get the root of this type of equation. So this type of equation could also be solved graphically in case you do not know about the Lambert W function. But many a time nowadays I see even in the Olympiads for math and so on, this kind of exponential problem is coming. And in that case, you can use the Lambert W function. Now let's come to question number 3, which is you are given a right angle triangle and the sides of this triangle are x, x square and x cube, and you are told to find x. So this is somewhat of a hard problem that it mixes aspects of geometry with algebra. So let's try to get into this. So in this case, you immediately know that Pythagoras theorem will apply. So I can write Pythagoras theorem here, which is x cube square is equal to x square square plus x square. So again, what I have done here is that I have taken the side here, x cube, I have squared it, and that will be equal to x square and x square square. So I get this important equation here. Now what I can do is I can expand this equation, take all the things to the left hand side. So I get this equation in a typical form which we like to solve, that is fx equal to 0. Now I can bring out x square from this particular expression, so I get this here. Now if you are solving equations, of course you can clearly see there are roots here. There is a root x is equal to 0. There are two of these roots, but that would correspond to the physical problem of there being no triangle, so we don't want to bother about that particular root. That's a trivial solution. So I look at the expression in the brackets, and that is x4 minus x square minus 1 is 0. And so I get this is the equation which we want to solve for non-trivial solutions. Now I can write x square as u, and if I do that I get this quadratic equation which is much more amenable to solutions. So of course if you remember the solution of quadratics, you will immediately know that u can be written in this form, that is minus b plus minus root b square minus 4ac by 2a. And so after I do that I get the solution as 1 plus minus root 5 by 2. So remember, here there is a 1 here, there is a 2 here, and here you have a 1 plus 4, that is becoming 5. Now of course if I look closely at this, I will see that only the positive root is going to make sense, because if I were to take the negative root, that is going to be a negative number here. So 1 minus root 5 is going to be negative, and therefore then u is going to be negative, and then x square, we don't want it to be negative. Again, remember, we are dealing with the real system. We have a triangle, so these have to be positive numbers. So I can take the positive value of u, that is 1 plus root 5 by 2, and so I get x is root of 1 plus root 5 by 2, which you can further simplify to 1.272. Now an interesting thing here is that what we stumbled on in this particular problem, the 1 plus root 5 by 2 term, it's something which is known as the golden ratio. It is quite ubiquitous as far as mathematics is concerned in many situations. And in the end screen, I'm going to put a link to my optimization class video about the golden section search method. So that is certainly a popular method as far as one-dimensional search is concerned in optimization. And in that video, I have also given some more interesting details about the golden ratio. It actually keeps cropping up in many situations, not only in things to do with architecture and so on, but also in nature and in natural systems. So now let's come to question number 4, and this is we want to find a function f of x where this function is given here, that is f x by x minus 1 equals 2fx plus x square. Now this is sometimes known as a functional equation, and again I see these being popular in many interview questions and so on. So let's try to solve this. So one of the ways, of course, to solve a functional equation is to take this value here, x by x minus 1, and to define it as something else. So we create a kind of auxiliary variable here or intermediate variable. And so we'll define u is x by x minus 1. Then I can, of course, write ux minus u is x. Further, I can write u is ux minus x, and I can write x is u by u minus 1. So essentially, I have now written x in terms of u, and if I substitute that in this equation here, I will get fu is 2f u by u minus 1 plus u by u minus 1 square. Now here there is an interesting step which we can take, is that we have to realize mentally that this is simply a function of some variable here. Now it can be u, it can be t, it can be y, it can even be x. So I can write this as fx is 2f by x minus 1 plus x by x minus 1 square. Now this is one equation which we have obtained through the substitution, and we also have the original equation here which I have written here now in blue. Now observing these two equations, I can clearly see that I could substitute this f x by x minus 1 into this equation, and that's what I do next. I take fx is equal to 4fx plus 2x squared. So all I have done is taken this equation here, which was the original equation which we have in red, and we have substituted it here, and that has helped me get rid of this complicated term which we do not actually want. So now after we do that, we get this equation here, and this equation is something which is going to give us f of x because f of x is there in this equation. So I take f of x to the left hand side, so I get minus 3 f of x, and on this side I get 2x square minus 2x plus 1, which is simply x minus 1 square, plus x square divided by again x minus 1 square term, which is x square minus 2x plus 1. And then I bring the negative 3 here. I can simplify this here. So essentially I will get a 2x4 term. I get a minus 2x cube term, and I get a term involving x square here, which is going to be 3x square. So this is the solution which comes out. So again 2x square into 2x is giving me this minus 4x cube term, and the term in the denominator simply becomes this expression multiplied by minus 3. So I have minus 3x square, this becomes plus 6x, this becomes minus 3. So this is the function here. Now if you are somebody who doesn't trust what I have done here, what you can of course do is you can go back and substitute x is x by x minus 1 and see what happens to this side. You should get this function back here. This was an interesting functional equation, and it tests the student's capacity to understand the fact that functions are general and they are essentially dependent on the variable concerned, and that you can change these variables at appropriate times. Now let's come to question number 5, which again is a popular question, and it actually forms the basis of a lot of things in applied mathematics, such as the Fourier series, the fact that many polynomials are orthogonal, and so on. And many a time this question is basically a very fundamental question. So here the question is that show that cos mx and cos nx are orthogonal on the interval x is minus pi to pi, and also m and n are integers here. Now, of course, we have seen that vectors can be orthogonal when their dot products are 0. And again, functions are orthogonal if when we integrate them on the interval specified, that is minus pi to pi, that should be 0 when m is not equal to n. So that's the condition for orthogonality. And the fact that the sinusoids are orthogonal is something which is the basis of Fourier series, because that helps you enormously in getting the Fourier series. Maybe we'll discuss that in a later lecture on these math problems where we look at Fourier series expansions of some functions. Now, this of course is an integration problem. You can immediately realize that if you need to get something like cos A into cos B, you need to extract a trigonometric equation here. And so we turn to the basic definitions of cos A plus B and cos A minus B. So cos A plus B is cos A cos B minus sin A sin B, and cos A minus B is cos A cos B plus sin A sin B. And I can see here that if I add these two, then the sine terms cancel out, and I am left with cos A cos B equals cos A minus B plus cos A plus B divided by 2. And so if I were to replace A by mx and B by nx, I get this equation here. Now, this kind of trigonometric identities are of course critical in calculus, and you need to remember these in the back of your head, because every now and then people ask these questions. Now, sometimes students say that why do I need to do all this rote learning? But remember, the person who is asking you the question, probably a professor, lecturer, or an expert in the field, they know these things as part of their general knowledge. So they are not going to be somebody who actually thinks this is rote learning. This is just natural knowledge, like knowing the capital of a country or knowing the president of a country and so on. So now we can write this integral in this form here. So this is very amenable to solution because we immediately know the integration of cos m minus nx and cos m plus nx, and we can write these out here, and the bounds are between minus pi and pi. We further solve this here, and again if m and n are integers, then we know that these are going to be 0, and therefore this integration is going to give 0 to us. So this is one of the things which is very important in Fourier series and in many situations where we take some function and we expand it out in a Fourier series, not only in terms of trigonometric functions, but there are even polynomial functions which are orthogonal. So probably we will look at some of those functions also. These functions are often used as basis functions, and just like there are vector spaces, there are also function spaces. And so very often we want to expand things out in these function spaces, because then the sequence which we have is often convergent. So that's something which is very useful, and very often they converge quickly. So that is something which is very important. So this was a set of 5 questions which I had for you today, and I hope you enjoyed this video. And if you have some different methods of solving these problems, please let me know in the comment section below. And if you already knew the Lambert W function, very nice for you. But if you didn't, I am certainly sure you learned something today. So I'll stop this video now. Please take a look at the different videos on the end screen to continue your journey into education and research and become a more knowledgeable person. And I will see you in a video sometime soon. See you then.